Have you ever wondered what the world was like during the final years of the dinosaurs? Not only to observe some of the most magnificent creatures this planet has ever produced, but to experience one of the warmest times in the past 500 million years. In this presentation, we will travel back 145 million years and outline the conditions of the final period where dinosaurs still roamed the Earth, the Cretaceous. We will discuss, in detail, the climate change during this 80 million year long period and how we can use it to better understand climate change today. Before we begin, we will discuss what exactly climate means, what the Cretaceous period is, and where it fits in Earth history. We will also talk about how discoveries made about the ancient world are interpreted by scientists today. So, what exactly is climate? You might say that climate is kind of like the weather, but over long periods of time. And it doesn't just account for the weather, it's a broad term used to describe a number of conditions related to the atmosphere and hydrosphere. And in case you forgot what those are, the atmosphere contains all the air, while the hydrosphere includes all the water. There are a couple other Earth spheres as well, like the lithosphere, which encompasses all the rocks, and the ecosphere, which contains all the plants, animals, and non-sciencey folks such as yourself. Now, you're probably thinking, okay, so we have the air, the water, the plants, the animals, the rocks, but that still doesn't explain exactly what climate is. Well, these Earth spheres all interact with and influence each other through complex processes such as the water and carbon cycles, erosion, and other mechanisms that you probably learned in 7th grade science. But in turn, these interactions result in long term global changes to Earth's temperature, humidity, weather patterns, and so on. But it's important to remember that climate represents an average of these conditions, and it changes over longer periods of time than the weather and seasons. Now, normally, these changes happen over very long periods of time, usually taking millions to tens of millions of years to notice any huge effect. However, as you may already know, in just the last couple hundred years, humans have indirectly caused the climate to change way faster than it normally does, and we call this process climate change. Now, a lot of people say that this super fast human caused climate change is a bad thing. And whether or not that's true, it's important to learn what past climates were like in order to fully understand what we're dealing with, particularly in regards to how the Earth and all of its spheres respond to changes in climate. And that is why today we will be focusing on how the climate changed throughout the Cretaceous period. Now, you probably already know that the dinosaurs all died out a long time ago, but to help you understand how long ago that actually was, here's a timeline of the entire Earth's history from formation to now. We won't talk too much about these first three because back then the Earth's climate was pretty unrecognizable compared to how it is today. But in short, it was really hot and there was no life for a while. And then life wasn't even really life as we know it until the Paleozoic, some 500 million years ago. As you can see, the Cretaceous period covers roughly 80 million years of Earth's history. Within this period, we have designated sections known as epochs and ages. When you look at rock formations around the world, you'll often see these layers, and when we look at those layers, some of which dating back to the early days of Earth's history, we will often see these distinct shifts in the types of rocks and fossils we see. Scientists use these changes to determine where the boundary of each epoch, age, or period should be. And now that we've covered some background information, let's move on to the topic of this presentation.
Climate change is observed throughout the duration of the Cretaceous. There are long periods of time where temperature remained relatively constant without much fluctuation, as well as sections in time where abrupt changes occurred. In general, two major climate events took place. We witness a steep spike in global temperatures here, which happens at the end of the Cenomanian. And we also see a general cooling trend during the late Campanian to Maastrichtian, which is here to here. Temperatures during this time fall nearly 10 degrees globally. As the figure on screen is shown, there is plenty of temperature change that occurred in the Cretaceous. But remember, we still need to consider many more factors beyond temperature when evaluating climate change, such as humidity, weather patterns, and so on. This leads into the question, how do we know what the climate was like? How and why did it change? This becomes even more difficult when considering the Cretaceous period occurred 70 to 140 million years ago. It is important to know where and what to look for. Luckily, for us, through the hard work and developments of modern science, all we have to do is read a few papers and next thing we knew, we were experts on the subject. To study historical climates, We utilize these things called proxies, which is a fancy science term that represents some measurable characteristic of past environments. This may be as simple as tree rings or as complex as an extensive rock formation. As it turns out, there are many proxies which scientists can study that will paint a picture of what the Cretaceous climate looked like. Here, we will explore some of these in further detail and showcase their importance to recreating historic environments and climate conditions.
Scientists often look at the rock record to develop a better understanding of past climates. They look for specific rocks that develop today only under certain conditions, and then when they are found in large amounts in the rock record, it allows them to infer that those same conditions existed in a similar fashion in the past. This method was especially useful when looking at the beginning of the Cretaceous period, where it was found that the climate transitioned from an arid, dry environment to being humid. We know this because we can see an increase in the amount of kaolinite in this part of the rock record. And since kaolinite is a type of mineral that only forms under the presence of warm and wet conditions, we can infer that similar conditions were present during this part of the Cretaceous. Dropstones and ice rafted debris. There's a good chance you never heard of these terms before, so for simplicity's sake, you can think of them like hitchhiking rocks that caught a ride on some floating ice. Then, after being dropped off by the ice, they end up on the seafloor, far from land. Dropstones have been found near the north and south poles in the first half of the Cretaceous rock record, indicating that there was frozen water, also known as ice, in these regions. This may come as a surprise, though, since the Cretaceous is commonly regarded as the warmest period of the last 500 million years. The oceans of Earth are home to many complex and interesting life forms, and they are even the foundation to all living things on this planet. Microorganisms, which have thrived in ocean settings since life began, contain valuable data in which we can analyze and gain information from. Without overcomplicating things too much, these tiny creatures host elements, and most importantly to scientists, oxygen, which can be found in different forms called isotopes. In this case, we will talk about two of them, oxygen 18, or heavy oxygen, and oxygen 16, or light oxygen. And depending on the amount of heavy oxygen relative to light, we can actually interpret the conditions of the ocean, such as temperature and sea level. These microanimals maintained their heavy and light oxygen from the time they died and became preserved in the seafloor, which we observe as fossils in the Cretaceous rock record. From this data, we can create temperature interpretations almost continuously from beginning to end of the Cretaceous. Additionally, the oxygen isotope data allows us to infer sea level, which was found to be constantly changing throughout the Cretaceous, and often, rising sea levels correlate strongly with rising temperatures. Beyond just the life in the oceans, the Cretaceous rocks themselves are an invaluable source of information. The oceans during the Cretaceous had experienced multiple ocean anoxia events, known as OAEs, which basically means that dissolved oxygen in the ocean depletes, potentially complicating things for marine life. In fact, OAEs have been connected to extinction events throughout Earth's history. But the two most significant Cretaceous OAEs occurred during the early Aptian and at the Cenomanian-Turonian boundary. We know that these happen because when we look at the rock record during these intervals, we see layers of organic rich, dark-colored rock which are indicative of anoxic events. These events are often correlated with increased volcanic activity, which will be explored in further detail later on. The continents are always shifting and moving around the Earth through a process called plate tectonics. We won't talk too much about why the plates move around so much, but essentially they move because they sit on top of the mantle rock deep within the Earth, which itself slowly flows around or convects. The position of the continents can have a huge impact on global climate, since as their position changes, ocean and atmospheric currents will change as well. This effect is most evident near the end of the Maastrichtian Age, which is known for its general cooling trend. As you can see from this reconstruction, this body of water, known as the Western Interior Seaway, is thought to have played a big role in transporting heat to and from high latitudes, contributing to the climate becoming more equable. But as the plates moved, the seaway closed, and now instead of a seaway that transports heat, we have a large surface of land. We call the ability for a surface to reflect light its albedo. Land has a much higher albedo than water does, meaning that it will reflect a lot more of the sun's light, resulting in cooling. Additionally, the seaway closing meant that new rocks were now exposed to the Earth's atmosphere, causing them to weather and erode. Weathering and erosion can play a big part in climate change because the atmosphere will interact with the exposed rocks, causing chemical reactions that suck the CO2 out of the air. And this leads us into. As you probably know, the atmosphere contains all the air that we breathe. This is mostly nitrogen and oxygen, as they make up 99% of all the gases in the atmosphere. But it's in that 1% of other gases that all the climatic magic happens. Maybe you've heard the term greenhouse gases, and maybe you've also heard that methane and carbon dioxide are the most common ones. Well, you'd be right. These gases have the effect of trapping heat in the atmosphere rather than letting it escape into space. So, in general, the more greenhouse gases in the atmosphere, the warmer our climate is. Spikes in atmospheric CO2 content can often be linked to intense volcanic events. In the Cretaceous, there were three of these. The Ontong Java, which occurred in two phases, first in the Aptian and second during the Cenomanian, and the Deccan Traps, which occurred at the very end of the Maastrichtian. We know about these not only because we can see the very large areas of volcanic rock created by these events, known as large igneous provinces, but because we can also see changes in osmium isotope ratios that correlate directly with the age of the volcanic event. Not only does the massive influx of carbon dioxide into the atmosphere result in warming, but it can also cause the oceans to become anoxic through complex processes involving oceanic organisms. Maybe unsurprisingly, the Ontong Java volcanic events happen right around the same time as the ocean anoxic events previously mentioned. The formation of these large igneous provinces has another potential effect. If the greenhouse gases released cause enough warming, it's possible for the Earth to enter what is called a hothouse climate. This is when the Earth is so hot all over that there is no continental glaciers. However, a hothouse Earth would be relatively short-lived, only lasting somewhere between 1 and 3 million years. And while we have used geochemical data to record long-term trends in CO2 abundance, we do not have records over short enough time intervals to confirm that the Earth experienced these hothouse conditions.
As we mentioned before, climate does change quite a bit throughout the 80 million years of the Cretaceous. Through the aid of multiple proxies, we can begin to develop a general consensus on the whys and hows when addressing the climate change of this period. For example, the abrupt increase in global temperatures during the Cenomanian was likely caused by the emplacement of the second phase of the Ontong Java igneous province. The volcanism released large amounts of CO2, enabling a greenhouse effect, which then, through complex interactions with the ocean's organisms, caused the oceans to turn anoxic. The general cooling of the Maastrichtian can also be explained through continental shifting, inland seas closing, and increasing exposure of rocks leading to weathering. The ability to understand the world as it works today allows us to better understand the past. Without question, there will always be limitations. Using proxies, modern science has shown the ability to look back into the past and better understand what the world was like over 70 million years ago. Through this process, we have gained valuable information not only of the Cretaceous period, but about our modern climate and the concerning changes that we face today.